All right, fine. So how do we actually go about calculating this? Now I bring back this idea. What I'm doing here with finding the area underneath the curve is doing integration. So integration is all to do with finding the area underneath the curve. Okay, finding areas underneath the curve. Okay, but I said right at the very beginning that differentiation and integration are just inverses of each other using the fundamental theorem of calculus. Fundamental theorem of calculus. Okay, so if I know how to differentiate, I know how to integrate. Watch this. This is just going to be a polynomial function, so I don't care about that at the moment. We'll talk about how we can integrate trig functions and exponential functions later. But let's do this. So if I start off with some function, can you just remind me of the process which you need to go through to find the derivative? So presuming this is like x to the power of n. Okay? What's the two-step process that I need to do to find the derivative function? So when I differentiate, what's the first thing I do?
Bring down the power.
Perfect. So the first thing I'm going to do is multiply by the power. Multiply by the power. What's the second thing we're going to do?
Decrease the power by 1.
Good. So subtract 1 from the power. We all happy with that? Mm-hmm. Good. Excellent. Now, I just said, right at the very start, fundamental theorem of calculus, all of this stuff to do with area is, for some strange reason, the reverse of differentiation.
Yeah.
Okay? So in other words, if this is differentiation, because integration is just the reverse of this, it just undoes this, I should just go back in the other direction. I should just undo this. Okay, so this is going to be integration. All right? So, if I'm going to undo this, what's the first thing I'm going to do? Exactly, do the reverse of subtracting 1.
So x over n plus 1 over n plus 1 or something?
Well, I mean, this is more to represent that's the derivative of that.
No. Do you think x over n, integration of x over n?
Yeah, good. So you can think about it like that. So x to the power of n plus 1 over n plus 1.
Yeah.
That's fine as well. Yeah, okay. But let's just think about it just in terms of a process, first of all. So if I've undone the subtracting one, now I just need to subtract, I need to undo the multiplying the power. Okay? So what's the opposite of multiplying by the power? Good. Okay, so add 1 and then divide by the power. Okay? So in other words, here is what I'm going to do. Here's what I'm going to do. I'm going to take my function. So I'm going to follow this idea, okay, to work this out. So if I want to work out the area, I'm going to integrate between -1 and 2. Okay, integrate between -1 and 2. That's my starting point. That's my end point. My y is given by this. That is just simply my function. Okay, so that's the height of each of these rectangles. Okay, x squared minus 6x plus 13. And then I just need to multiply by some infinitesimally small change in x. Okay, it's more notation. Okay, so then I just follow through this process. Okay, so this process says I need to first of all add 1 to the power. Add 1 to the power. So if I add 1 to the power, what do I get? So just treat it term by term. What if I add 1 to x cubed? What do I get? Yeah, so I'm going to add 1 to the power, and then I'm going to divide by that power. So the power is now 3, so I'm just going to divide by 3. Make sense? Okay. Do the next one, minus 6x. Add 1 to the power. What do I get?
1 over 6.
Good. And then I'm going to divide that by that power. So 6 divided by 2 is 3. Does that make sense?
Yeah.
Yep, good. And then, have a think, 13. What's the power of x at the moment? Good, it's x to the power 0, yeah? So it's going to be x to the power 0 here. Just hiding there, right? So if I add 1 to the power, what do I get? Just x, right? And then I divide by that new power, hence I get 13 over 1. Does that make sense? Hang on a minute. Yeah? However, I'm not quite finished. Because I said that integration is the reverse of differentiation. So have a think. If I differentiated this function, would I get back to here? Sort of. Okay, if I differentiated that, I definitely get x squared. If I differentiated that, I definitely get negative 6x. If I differentiated that, I definitely get 13. However, I could also have a number here. I could have like plus 5 or plus 7, just plus some constant, plus some number. Because of course, if I differentiate a constant, I would get a plus 0. Okay, so I've got to almost imagine there's a plus 0 hanging around there. Yeah? So that's the reason why I add a plus c if I need to do my integration, because I don't know what that number is. So reverse of integration is a reverse of differentiation, but I don't know what that number was. Okay? All right, fine. So now I've done my integration, I just put that between two brackets, and then I think about these limits here. So negative 1 to 2. All right? Negative 1 to 2. This thing here, okay? You remember when you differentiated a function, you've got the gradient function. When you differentiate, you've got a gradient function. In other words, it says, you give me the value of where you want to find, and I will tell you what the gradient is at that point. Yeah? Okay? This now, because we're now talking about areas, this now is an area function. In other words, it will tell you the area from the left all the way up to the point which you stick in. Okay? So if I have a function that looks like this, okay, and if I stick in, say, for example, if I stick in, for example, 3, what this function will do, if I stick 3 into this function, it will tell me the area underneath the graph all the way up until 3. So from negative infinity all the way up till 3. That's not what I want here. I want the area up until 2, but I don't want the area below negative 1. Okay? So the way that I can get around this is by sticking 2 in here. So I get 2 cubed over 3 minus 3 times 2 squared plus 13 times 3 plus c. Okay? And then if I take away the area which I don't want, which in other words is the area all the way up until negative 1. So I've stuck 2 in there. It's going to give me the area all the way from negative infinity to 2. But then if I stick negative 1 in, it'll give me the area up until negative 1. I don't want that, so I'm going to take it away. All right? So I'm going to take away this thing. So negative 1 all cubed over 3 minus 3 times my negative 1 squared plus 13 times my negative 1 plus c. Okay? Now, can you see that the plus c's are effectively just going to cancel out? Plus c's are gone, yeah, because I'm going to take away c. Can somebody stick this in a calculator and tell me what they get? Have we tried it? 33. All right. So there you go. There you go. So, just to recap, we said that our area, just by considering sort of rectangles, okay, we said that our area was going to be approximately 41. However, we knew that was going to be an overestimate.
Yeah.
Yeah? By thinking about this idea, by thinking about sort of infinitesimally small change, in other words, by thinking about areas or sort of rectangles which were infinitesimally small, then we were able to use this idea by thinking about the reverse of differentiation, and we found that our actual area, the true area, was 33. Does that make sense? Okay, good.